So this is Chapter 7, Section 1. Like I said, it's broken into two parts. We'll cover Ionic Nomenclature in the first half, Part A, and then in Part B we'll do Molecular Nomenclature, which is all of the covalently bonded compounds. For Ionic Nomenclature, you've got your ionic formulas. We're going to talk about what are the rules or steps. It's not so much steps, it's just a collection of rules, really, that you need to think about whenever you have a formula given to you and you've got to come up with the name, or what if the name is given to you, how do you come up with the formula? When I say formula, I'm talking about all the letters and subscripts, subscripted numbers. So for ionic formulas, you'll write each ion, cation always comes first. If I ever give you a formula for a compound, that's just how it's given to you, is the cation first, then the anion last. And remember, if I'm giving you compounds, they're considered to be neutral, so all your positive and negative charges cancel out. Just remember, all of your charges have to cancel at some point. You never ever show charges in a final formula. And here's what I mean about that. If I were to give you the formula or told you water and you come up with H2O, even though you've memorized hydrogen has what charge? 1 plus, and oxygen has what charge? A 2 minus, okay? You would never put any pluses or minuses or superscripted numbers ever within a neutral formula. And that's the only thing that we're working with. So it's just H2O. Now, overall charges have to be equal. If your charges cancel, that's great. You just write down the symbol. So if you have hydrogen with a 1 plus charge and we'll say fluorine with a 1 minus charge, because those charges cancel, you just write down the symbol. But if your charges do not cancel, then you have to use subscripts to balance charges. You've got to use subscripts to balance charges. This right here is where we get into, with this second bullet, that's what we call the crossover method. And I will teach you the crossover method today, but the crossover method is where you take charges that are not alike and you take them as superscripted numbers and they cross over to become your new subscripted numbers. Superscript, what does the super mean? The numbers are above. And if I say subscript, the numbers are where? They're below, or they're at the bottom of the formula. So I will teach you how to do the crossover method. I suggest, until you get really comfortable with this, that anytime you see a polyatomic ion, you put parentheses around it. I will never count off in this class if you put parentheses around a polyatomic ion, even if it's not necessarily required. Okay? But some of those polyatomic ions, like the ones that you're memorizing, we'll say, for instance, I know I had written one up on the board, but we'll say NH4 plus. What's the name of that ion? Ammonium. The ammonium ion. Do you want to lose it? What you're trying to get out of your pocket?
I'm trying to fix it in my pocket. I'm sorry.
I hope it doesn't require exit out of your pocket.
Promise it doesn't. Promise that I will not leave my pocket.
Okay. NH4, I would put parentheses around this right here and the pluses on the other side. This is so that when we do the crossover method, that 4 that's outside the hydrogen doesn't accidentally get moved somewhere. Okay? So, again, until you get comfortable, I suggest you just put parentheses around all of them. What is the name of this one? Carbonate. Okay? CO3 is carbonate. It's got a 2 minus charge. That 2 will get moved somewhere. That 3 will not. Okay? So those subscripted numbers that are part of the polyatomic ions will never move. They'll never move. Only your superscripted numbers. And we introduce you to what's called the stock system. This is where you have Roman numerals. And you noticed at the bottom of your monatomic ion sheet that several of those transition metals had Roman numerals, right? Okay. Roman numerals indicate the ion's charge. And I had already stated, for instance, there was copper Roman numeral 1 and copper Roman numeral 2. So if I ask you tomorrow copper Roman numeral 1, you're going to write down what as the symbol in charge? Cu with copper Roman numeral 1. It would be a 1 plus, okay? If I asked copper Roman numeral 2, you would tell me Cu with a 2 plus. So the Roman numerals are important. You put them when they're required, but if they're not required, like on your sheet, if you look at your monatomic ions that should be there in front of you, do you see any Roman numerals next to sodium? No. Do you see any next to zinc? No. Do you see any next to aluminum? No. Do you see any next cadmium? No. So if there's no Roman numerals, it's telling you that's its only possible charge. If we were into a much higher level of chemistry, there's even going to be a couple variations from what you see, but for right now, we're going to go based on the paper that you have in front of you. Okay? So you can't randomly add Roman numerals where they're not supposed to be. Now, that is if you have the name or the formula going to the name. What if we have the name or the formula? I think I said it backward. This part is ionic names, but you're actually got the formula going to the name. The previous one was name to formula. Did I just say the same thing again?
I don't know what you're
talking about.
Well, we're going to go back. All of these right here. If I'm looking at it, because I think I'm saying the same thing, it's talking about writing down the ions, we're crossing over charges. This right here is if you have the name given, and you're going to the formula. Because I think I just kept repeating myself all ago. Name going to the formula. That's all the things that you need to keep in mind. Now, on the next slide, it's going to be things you need to keep in mind, but in the opposite direction. This is going to be if you have the formula given. Formula, that means letters and numbers. Formula is given, and you're going to give me the actual name. So always write the name of both ions. Cation comes first. Now, when they say both ions, that could be two polyatomic ions. It could be a cation and an anion. It could be, it's definitely going to be ions, but just know it could be a cation with a polyatomic ion. It could be a polyatomic ion with an anion. All of them are ions, but you're going to have opposite charges of some sort. Cation, which is which charge? Cations always come first. That's the positive charge. Now, if your second ion is a monatomic ion, that means your second ion, being monatomic, has to be an anion. The ending is always "-ide". The ending is "-ide". If your second ion is monatomic, that means it has a negative charge. That's why I'm putting anion. The ending is "-ide". So look at your monatomic ions right now. Look at all of those that have negative charges. What's the ending for every single one of those with a negative charge? I to E. You got fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, okay? Phosphide, any of those with a negative charge, they end in IDE because they would appear at the end of your formula anyways. If you have a polyatomic ion, then you have special names that go with that. So if I'm looking at a formula, if my formula, for the most part, has 3 or more elements, I'm identifying what the polyatomic ion is. So for instance, if I gave you this formula, If I gave you this formula right here, how many different elements do you see?
3.
3. Sodium, carbon, and oxygen. That means 2 of the 3 have to make up a polyatomic ion. Guys, look at your polyatomic ion page. How many of those polyatomic ions, and there's about 35 or so, how many of those have a positive charge?
2.
2. The rest are negative. So the majority of your polyatomic ions are going to come at the beginning or end of your formula. The end. And I can tell you right now, the only polyatomic ion I'm going to give you that with a positive charge is going to be the first one. Ammonium is very common. The dimercury, not so much. So, Na, C, and O, which 2 make up a polyatomic ion? The sodium, the carbon, oxygen, which combination makes up a polyatomic ion? We just looked and I just said there's really only one with a positive charge that would come at the beginning. It would be the CO. We're looking for stuff at the end. And the last 2 elements are the carbon and oxygen. It's really CO3, right?
Yeah.
Okay? So, to be on the safe side, I would put parentheses around that and figure out what is its special name. Okay? So, you're going to identify if there's a polyatomic ion before you go any further. And the last thing, if we have a metal that needs Roman numerals, you're going to have to figure out how to come up with the Roman numeral. We're calling that, or I call it, the weather pattern. Weather pattern. Weather pattern. And I'm sure there might be another name for it. That's just what I call it because it reminds me of the weather cycle. Now, on the next slide, it's going to give you, there's tons of little rules here and there. The next slide is going to give you things to consider. Again, if you only see 2 elements, the ending is "-ide". Okay? If there are 3 or more elements, it probably ends in "-ate" or "-ite", which are polyatomic ions. Look at all of your polyatomic ions. Give me, of the 35 or so, which ones do not end in "-ate" or "-ite"?
2.
Ammonium. What else? Hydroxide.
Dimercury.
Dimercury,
Peroxide.
which I'm not counting. Peroxide. Cyanide. Cyanide.
Oh, yeah.
Okay, I think those are the only 4 that don't end in "-ate" or "-ite". The rest end in "-ate" and "-ite", so pretty easy to keep those. If you see the ending "-ate" or "-ite", automatically go look and see, okay, can I find my polyatomic ion? If you see 3 or more elements, go look for the polyatomic ion. Okay? Roman numerals. If you see a Roman numeral, that indicates charge. If you see a metal that might need Roman numerals, we're going to show you how to go back and figure out what Roman numeral it needs with this weather pattern. And it says no prefixes here. You've not learned about the prefix system yet, which goes with molecular nomenclature, so it shouldn't be a problem for tonight's homework. But no prefixes ever, ever, ever. And here's what's going to happen. Some of you are going to get really comfortable with the prefix system when we cover molecular nomenclature because it is so much easier, and you're going to want to use prefixes on everything. And so you'll be wrong 75% of the time. Okay? So just highlight that so that you don't make that mistake later. Common ion charges, we've looked at this before. Group 1 has a 1+. You can look at your monatomic ions and see that. Group 2 a 2+, Group 13 3+, Group 15 3-, then 2-, then 1-, and then your noble gases don't have a charge. Y'all already knew this though, correct? Okay, so you've got your monatomic ions and polyatomic ions in front of you. Let's look at these examples. I say don't look at the answers yet. If you just want to watch up here, don't look at the answers yet so I can show you how I would go about solving these. First one, potassium chloride. If I'm looking at my examples, first off, it ends in IDE, right? So chances are there's no polyatomic ion, correct? What is the symbol for potassium? And what is its charge?
Plus.
It's a 1 plus. What's the symbol for chloride?
C.
And what is its charge?
Minus.
1 minus.
Stop.
Do those charges cancel? Yeah. 1 plus plus or minus 1, that's 0. That's what I mean by do the charges cancel. And they do. And it tells you if the charges cancel. So if you just write those down, your answer is KCl, potassium chloride. Notice the cation was listed first in the name, the anion is last. That is typical. Magnesium nitrate. The first thing that points out to me is, oh, ATE. I have a polyatomic ion here because I see that ATE ending. You know, hopefully from memory by tomorrow, nitrate. What is the symbol in charge for nitrate?
3.
It's NO3 with a 1 minus charge. 1 minus charge. I would put that 3 in parentheses because I don't want you moving the 3 anywhere. Magnesium has what charge?
Plus.
It's a 2 plus. Now, a 2 plus and a 1 minus, do they cancel? No. So here's what I mean by crossing over charges. That 2 is superscripted. It will come over and become your new subscript. The 1 will come over here and become your new subscript over on the other side. Okay? So I would write down Mg. The number 1 comes behind it. And then you've got NO3, and the 2 goes behind it, correct? If you don't put the parentheses and you write it like that, it's going to look like you have 32 oxygen, which is wrong. So, put the parentheses, right like that. That is telling you you have 2 nitrate ions. So, to be electrically equal, 2 nitrate ions are needed with 1 magnesium ion. Now, 1s are understood as subscripts. If you have identified the symbol, in this case magnesium, and there's only 1 ion of it, I do not write the 1. So I'm erasing the 1. Copper 2 chloride. I don't see ATE or ITE, but I do see some Roman numerals. So the symbol for copper is Cu. What is its charge?
2 plus.
2 plus. And you did not look at your monatomic ions to answer that, because charge and Roman numeral, that's the same thing. Chloride, that's Cl with a 1 minus. Do those charges cancel? No. So we're crossing over charges again. The 2 over here, the 1 over here, which is understood. You end up with CuCl2. CuCl2. Who's got a question? So just realize every single time in these examples we looked at charge, we went from name to formula. You have to look at charges, and the majority of the time you're going to cross over charges because they won't cancel. Look at charges, cross them over. Now, what if we go the other way? We've got formula to name. The first thing I'm going to look at in each one is there a polyatomic ion? That's number 1. And number 2, am I going to need Roman numerals? So, in the first one, is there a polyatomic ion? How do you know there's not? No. How do you know there's not a polyatomic ion? There's no charges in any of these. There's only 2 elements. Okay? What's the name of the first element? Well, it's sodium. And the second element is bromide with IDE ending because it's the anion that comes at the end. IDE. And the next one, is there a polyatomic ion? How do you know there is one? There's 3 elements. Which 2 of the 3 make up the polyatomic ion? I think I wrote this down as the example earlier. What's the name of CO3?
Carbon.
It has its own special name, carbonate. And then you give the name for Na, which is sodium. So those two weren't bad because that is from memory. Okay, you're memorizing what the names of these different elements are. The last one's going to be just a little bit more difficult. Do you see a polyatomic ion? No. So let's give the names for what we see. What's the name for Fe? It's iron. What's the name of Cl? Chloride. The other thing you've got to think about is, look at your metal. Is it one that needs Roman numerals? So for memory, you've memorized iron can be Roman numeral.
3.
Well, not all of them.
1, 2, 3.
A 2?
And 3.
A 3?
Or 4.
Or 4? Is it listed 3 times on yours?
It can't be a 4. It can't be a 4.
Okay. Well, on that paper, yeah. Okay. But it's got more than one. So here's what we're going to do. I'm going to put parentheses right there because the Roman numeral's got to go there. I'm going to show you this weather cycle pattern thing that I do that works 100% of the time. There is a shortcut to this that only works 80% of the time. So I say you learn my way, so there's never a question if you're going to have it right or not. I'm going to put a box right here above iron. And I'm going to, basically I'm splitting this right between the cation and the anion. We're going to work on the anion side first, and then we're going to move around to the cation side. Start here. Step number 1. And I will have several of you that can't remember what to do and where to start. So I'm telling you, write this down. Step 1, what is the anion's charge? You're writing that down. What is the anion's charge? That's step 1. In this case, what is chloride's charge? That's from memory. Chloride's common charge is what? Positive or negative?
Negative.
Well, if it's at the anion, it's got to be negative. So -1. That's step 1. Step number 2, you are going to multiply that charge times the subscript on the anion. Multiply the charge times the subscript on the anion. So what is -1 times 3? -3. Our goal with all of these numbers we're going to put at the bottom, this is going to be step 3. Our goal at the bottom is to make sure all of these numbers add up to be equal to 0 because we're dealing with neutral compounds. We're dealing with neutral compounds, so that means 0. Step number 4, you figure out what number do you add to a -3 in this example to get 0. +3. Step number 5. Now we're going to move back up.
Wait, what was 4?
Step 4 is you figure out what number do you add to that other number at the bottom that we have in yellow this time to equal 0.
What was 3?
All the numbers at the bottom equal 0. This is for neutral compounds. Step number 5, you divide the number below your cation by the subscript of the cation. Divide the number below the cation by the subscript of the cation. What subscript is with iron? It's an understood 1. What is +3 divided by 1?
Plus or -2.
What is +3 divided by 1? It is 3. +3. That is the Roman numerals that are going to go over here with iron chloride. Guys, once you get used to doing all these little steps, it's going to be a no-brainer to you, I promise. But a lot of times, it's kind of like when we were doing Lewis structures, and I said usually if people mess up, it's with the very first step, just counting up electrons. Same way with this. People usually can't remember what's the very first thing I do? They remember I multiply and I divide, but they can't remember that first step, which is find the common charge of your anion. So the answer to that is iron 3 chloride. We're going to do one that's a little bit harder. Same thing, but going to be a little bit harder. Yeah.
Step number 5.
Divide your charge below your cation by the subscript of the cation. Okay, let's go work out another example. That hurt. Okay, let's say that I give you... I'm going to give you one where if you don't do it the way I did it, and here's... Let me show you what that... well, I've erased it. Notice on that iron 3 chloride, this is what a lot of people want to do is shortcuts that don't work every time, is they see the 3 here, and a lot of times this number, that 3, becomes the Roman numeral. They back cross charge. Instead of crossing over charges, they just go backwards. Okay? Works 80% of the time. Let me show you an example where it will not. Oh, I don't want to use iron again. How about... I'm giving y'all the wrong thing. S-N... Okay. We're trying to come up with a name for this right now. So what's the name for SN?
10.
It's 10. What's the name for CO3?
Carbonate.
I was really nice and even put that in parentheses for you. Carbonate. Does 10 need Roman numerals? Yes, it does.
How do you know if it does or not? Oh,
You're memorizing the chart, and 10 had multiple charges. Now, we're going to set up just the way we did earlier. I'm going to put my box right here, and I move. The reason why I call it the weather pattern is because we move in a clockwise direction. We're going to do here, then here, then here, and back up here. So we just make one big circle. Okay? What was the very first step for you doing this weather pattern to try to figure out what's the charge?
what's the charge of CO3?
What's the charge of the anion, CO3? What is CO3's charge?
+2.
No.
-2.
-2. Guys, that is for all of CO3, and it's in parentheses. Even if it were not in parentheses, I would want you to put it in parentheses at this point so you don't do something crazy with the 3. Okay? And you will have examples where your polyatomic ion is not in parentheses because it's not needed. What do I do with that -2?
You multiply it by that 2.
We multiply it by the 2. So see, if there were no parentheses there, you're going to want to multiply it by the 3 accidentally for a different formula. So -2 times 2 is? -4. I'm going to keep going because we want all of these numbers on bottom to equal what? 0. So what number do I add to -4 to get 0? +4. And then we divide going on our way back up. It is +4 divided by 1, which is 4. So that is our Roman numeral, IV, which is 4. So what?
Do you always divide it by 1?
Well, you divide it by whatever subscript is with the cation. And in both examples, it's been an understood 1. But if that would have been a 2, 3, 4, something like that, you divide by that number. Yeah.
I have a question. Would it ever be an odd number to where you'd have a decimal?
No,
Okay.
never.
And then is the cation always going to come first?
Yes.
Every single time.
Every single time. That's all you know? Okay.
Yep. Cation's always first. There is one minor exception to that, but when we get to acids, we'll talk about it. Notice on this one, notice how I showed you FeCl3. We took the 3 and just backtracked, and that was the Roman numeral. Notice you couldn't do that in this case, right? Here's why you couldn't do that in this case. This is something else that you need to know. So we were dealing with charges of 4 plus on the tin and 2 minus on the carbonate. When you cross over those charges, notice we didn't have a 2 here and a 4 here. What did we actually have? Instead of a 2 and a 4, when they crossed over, what happened?
You had a 1 and a 2.
Because why do you think that is?
They reduced.
They reduced. So when you have charges like this is for your information when you're going the opposite way. And these charges don't match, so they don't cancel. But in an ionic compound, if you can reduce them, you reduce them before you cross over. So a 2 and a 4 does reduce to a 1 and a 2. Got it?